All right, so for this video, we are going to be talking about exponential functions. So we're going to talk a little bit about evaluating exponential functions, a little bit of negative exponents here, but more specifically, we're going to talk about how do we graph exponential functions, and then how do we work with like exponents when it comes to different problems, specifically simple interest, compound interest, just different types of interest and that type of things that do tend to have a lot of different exponent components and stuff in those style of problems. So let's go ahead and jump right into it. An exponential function is a function in the form f of x is equal to a to the x. We don't want a to equal 1. If a equals 1, you're just talking about 1 raised to powers of something, which is typically just going to give you a 1 right back. So our base is going to be a number with our exponent typically holding our variable in it. For your parent function here, the domain is set to negative infinity to positive infinity. So we're going to get just a little bit more information into what some of these graphs and these functions really do truly entail. But for right now, we're going to kind of just focus on, a function given to us in exponential form with the base being a number raised to some power of x here. So real quickly, just to make sure that we do remember how to work with exponents and things of that nature. Our first three examples here, we are told that f of x is equal to 1/4 raised to the power of x. Evaluate each of the following. So for each of these, well, for a, we're doing 1/4 raised to the 0. Then we're going to be doing 1/4 raised to the 5/2 over here. And then f of negative 3/2, so we're going to take that 1/4 and raise it to a negative 3/2 there. Now, depending what school, what class you are taking this for, a lot of times at this level here, you are allowed a scientific calculator. If you are allowed a scientific calculator, that is a great option for you to use here, because in that sense, then I can just put the 1 divided by 4, so that is our 1/4 as our base, and then just raise it to a power. Now, keep in mind, anything raised to a 0 power is 1. That is one of the basic exponential rules there. So 1/4 raised to the 0 power is simply just going to be a 1. 1/4 raised to the 5/2. So I'm just going to plug that in right in here. 1/4 raised to the 5/2 we see is going to get us 1/32. Now, real quickly here, if you are working this problem by hand, anytime you are taking a base, raising it to a fractional exponent. So the number in the denominator is actually your index for this. We have a 2 here, which means what this is really telling us, this is really the square root of 1/4. So this is the square root of 1/4. That's what the 2 tells us, that this is going to be an index of a 2 here. Right? If this were a 3, it'd be a cube root. A 4, it'd be a 4th root. The numerator is the actual exponent for this portion here. So we're going to take the square root of 1/4. Then we are going to raise it to the 5th power is what this is asking us to do here. So if we take the square root of 1/4, that does give us a 1/2. And then if we take 1/2 raised to the 5th power, that's then going to give us the 1/32. So whether or not you're allowed a calculator, this is definitely a workable problem here. So for example, C, you're taking 1/4 raised to the negative 3/2 power. So you're either just throwing that into your calculator, or our denominator is a 2. So that is telling us to take the square root of 1/4. And then we're going to raise it to the numerator, so a negative 3 here. So whether we type that into the calculator, whether we work this by hand, we will get an 8 here when we simplify that. So one of the first ways that we learn how to graph exponential functions is literally just by plugging into a given table here. So for this next example here, so let's sketch the graph of f of x is equal to 2x by first completing this table of values here. So to fill in the spots here, we're just going to do 2 to the negative 3rd, 2 to the negative 2nd, to the negative first, to the 0, to the first, to the second, to the third. So if we plug in a negative 3 here for x, 2 to the negative 3 is a 1/8. 2 to the negative 2 would be a 1/4. 2 to the negative 1 would be a 1/2. Anything to the 0 power is a 1. Well, 2 to the first is a 2. 2 squared is 4. And 2 cubed is 8. So let's see what this graph would look like if we plot these points here. So for our first point, we have negative 3 and a 1/8. So if we go left 3, 1, 2, 3, a 1/8 is actually about a positive 0.125 there. So it's going to be right above that line there. For negative 2, we have a 1/4. So it's just going to be a little bit higher here. Negative 1, we're going to have a 1/2. At the 0, we're going to be at a 1. Then we're going to have 1, 2. We're going to have 2, 1, 2, 3, 4. And we're going to have 3 that's going to go all the way up here to 8 here. And let's connect those dots. So when we connect these dots, this is what a increasing exponential function looks like. When you look at a graph, you want to look at a graph from left to right. And going left to right, this graph looks like it's hugging that 0, that x-axis right over here. And we see that it starts to curve up pretty darn fast here. So it is curving up exponentially here. So this is what an increasing exponential function looks like here from left to right. It is shooting upward pretty fast there. For our next example, let's go ahead and sketch the graph of f of x is equal to 1/2 raised to the x power. So I'm sorry, that x gets thrown off a little bit there in formatting. So 1/2 to the x power. So we're just going to take these values here. We're going to plug it into x. So the first value here is going to be 1/2 raised to the negative 3. Keep in mind with negative exponents, if you are taking a fraction and raising it to a negative power, what that's telling you to do is flip that fraction, and you are now raising it to a positive power. So this is really 2 cubed over 1 cubed, which is just an 8. If you need a little bit more practice on negative exponents, I do have a video that focuses solely on negative exponents. I recommend pausing this video real quickly, maybe going and watching that real quickly, and then coming back to this. So when I went ahead and filled out the rest of them, 1/2 to the 4th, and so on. There are our values for those. So let's go ahead and start to plot these here. So we have a negative 3, and we have an 8, which is going to be up here. We have a negative 2 and a 4. Then we have a negative 1 and a 2. I'm sorry, I did 1/2 to the 0, should be a 1. I'm not sure why I wrote a 0 there. So we should have a 0, 1. Then we're going to have a 1 and a 1/2, a 2 and a 1/4, and a 3 and a 1/8 here. If we connect these dots, this is what this looks like here. This is called a decreasing function. Notice going from left to right, this graph is rapidly getting closer and closer to 0, and it is going to continue to just hug that line right over there. It's actually very, very similar to our other graph here. Right? If you compare these two here, right, increasing function, decreasing function, they're almost kind of just flipped versions of each other. Now on this next page here, so it's kind of just some random information about an exponential function. If we were looking solely at the parent function here, so your domain does tend to be always negative infinity to positive infinity here. The range is from 0 to infinity. If you did note for our previous two graphs there, right, both of these were above 0. Now we are able to have transformations on this function here. We are going to talk about that slightly. So we are going to be able to take this graph and move it around, right? Shift it left, shift it up, shift it down. So we will start to see values there. But if we're just talking about our parent function with no transformations, we do have arrows on either end. So our domain is negative infinity to positive infinity, with our range going from 0 to positive infinity there. So technically in my brain, I always think of this as if a is greater than 1. All right, so if a is greater than 1, you are talking about the growth factor, which is an increasing function there. So that's the one that goes this direction. If your base here is between 0 and 1, you are talking about that decreasing function that goes in this direction here. So kind of just some extra things about it. Notice for our two graphs, we did not have any x-intercepts. They did not cross that x-axis there. So unless we have transformations on that, we will not see x-intercepts for our graph. The y-intercept does tend to be 0, 1, and it was 0, 1 for both of those graphs. Some of these other pieces I will refer to back here in a little bit whenever we do need to address some of these issues here. Though we are just going to start off, so this video we're going to focus on sketching exponential functions. We will get further into detail with more complex examples in a different video. So right now we're just learning the basics. We're learning how to plot these. We're learning how to input these. Learning some of just the basic things about exponential functions here. So if we take a look at this next example, we're going to use transformations to sketch the graph of f of x is equal to 2 to the x minus 1 plus 3. So if we take a look at this function there, we did talk about graphing already. F of x is equal to 2 to the x. So that's this graph right over here. So the difference between this and this one here, right? So this one was f of x is equal to 2 to the x. We now need to graph f of x is equal to 2 to the x minus 1 plus 3. So we're taking a look what this is telling us here. So think about this. If you remember, if you happen to remember the vertex form of a quadratic equation, most students are somewhat familiar with quadratic equations, just a little bit more. And when it comes to quadratic equations, if there was a plus or minus number on the inside of the parentheses here, that meant a horizontal shift. You always did the opposite of what it said. If it said minus 3, you would go to the right 3. If it said plus 2, you would go to the left 2. The number on the outside at the end of your equation here is a vertical shift. So you do exactly what that says. If it says plus 2, up 2. If it says minus 5, you're going to go down 5. So kind of taking that into consideration here, we have, think of our exponent as being the inside of the parentheses. If we have an x plus or minus number here for our exponent, that signifies a horizontal shift here. So x minus 1 is telling us that we're going to take this graph and we're going to shift it to the right 1 unit. Whatever number is at the end over here, plus a number, minus a number, if it's plus a number, you're going to shift it up, however many units that says. If it's minus a number, you're going to shift it down, however many units that says. So in comparison to 2 to the x, we are going to move right 1. Right, if it says minus 1, that means right 1. It says plus 3 here at the end, so that's going to mean up 3. So from this graph, let's go to the right 1 or up 3. So I'm going to take these points here. All right, so our first point was a negative 3 and a 1/8, which is about right there. We want to go to the right 1 time, and we want to go up 1, 2, 3. For negative 2 and a 4th, right 1, up 1, 2, 3. For negative 1.5, again, right 1, up 1, 2, 3. For 0, 1, we're going to go to the right 1, up 1, 2, 3. Then we had 1, 2, so we go to the right 1, up 1, 2, 3. Then we had 2, 4, so we go to the right 1, up 1, 2, 3, 4. And then we had 3, 8. That's going to run us a little bit past that I can draw here. So this is about what our graph is going to look like. It looks exactly just like the other one. Shifted to the right 1 time, shifted up 3 times. So that is one option you have to use in using transformation in order to sketch this graph here. You do happen to see f of x is equal to 2 to the x power. It is a pretty common exponential graph, so you will tend to get used to that style of graph and understand how to shift it. Your other option that you do have for graphing is you can take this function here, build your own little table here. If we need to graph this, we can plug in for x and then create our own values, just like we did with the previous two examples here. Start plugging in x values. Plug in a -2 for x, plug in a -1, plug in a 0, plug in a 1, plug in a 2, until you feel confident enough to be able to sketch your graph. Plug in values for x, get those values so that you can plot the point, connect the dots. So that is always an option for you to graph here. Now, for our next example here, we're going to find the exponential function of the form f of x is equal to c a to the x power, whose graph contains the following 2 points here. So what they're asking us to do is they're asking us to take these 2 points and create the equation, the exponential equation based off of those 2 points. So we are going to take our f of x is equal to ca to the x. And one of the first things I'm going to do is take this out of function notation. Remember that f of x is equal to y is equal to f of x, right? So these two represent the same exact thing. Go ahead and plug in our first point here. We're going to plug in a -2 for our x, a 16 for y. That is going to look like 16 is equal to c. We don't know what that is. A to the x, which is a -2. Solve this for c. Now, when we solve this for c, in order to get rid of a to the -2 on each side, what I'm going to actually do is multiply by a squared on each side. Now, the reason why I'm going to do that is remember the product rule for exponents. A to the -2 times a squared. You're going to add those exponents. -2 plus 2 is going to make that cancel out on the right-hand side, and that's going to equal c, to where c is equal to 16a squared. After that, what we're going to do is, again, we're going to go back up to our given function here. F of x is equal to c to the ax. Now, let's go ahead and plug in c here. So f of x is equal to, well, c, just this piece here, is 16a squared times that a to the x here. Now, our next goal is going to be to try and figure out what is a so that we can build the full equation here. In order to actually create this equation, we need to know what c is, we need to know what a is, x is going to stay there. So what we're going to do is we are going to use our next point here. We're going to use the 3 and the 1/2, and we're going to plug it in here. So keep in mind, f of x is our y. This is going to look like a 1/2 is equal to 16a squared times a to the third. Now, let's work on solving this here. So we're going to have 1/2 is equal to 16a to the 5th. Again, product rule all over again. A squared times a cubed is a to the 5th here. Divide both sides by 16 here, which is going to leave us with 1/2 divided by 16 is 1/32, and that is going to equal to that a to the 5th. Take the 5th root of each side, and a is equal to 1/2. All right, the 5th root of 1 is going to be a 1. The 5th root of 32 is a 2, so you do get a 1/2 there for a. Now that we know the actual value of a, going back over here to this equation we can actually find the value of c. We can use 16. We're going to plug in 1/2 here for a, and we're going to square that to get c. Now, 1/2 squared is a 1/4, and a 4th of 16 is equal to a 4. So 4 is equal to c, a is equal to a 1/2. So when we create our equation here, f of x is equal to c, which is a 4th, times our a, 1/2, raised to the x power. For our next example here, so let's see, it says Juanita has deposited $10,000 into a bank at a simple interest rate of 7.5% for 2 years and 3 months. How much interest will she receive? how much money will be in her account at the end of the 2 years. So we're going to jump into our interest problems, also kind of sort of known as banking math here. These are very, very applicable problems to the real world here. Anytime you're trying to invest, maybe anytime you're taking out a loan or anything like that, a lot of this stuff applies. So it's really important to, know some of this information to possibly be able to calculate it yourself, just to make sure that you might not be getting screwed over when it comes to certain things, or to understand what are better investments, what are, better savings, and just different things like that. So we're first going to talk about simple interest. The formula for simple interest is equal to the principal times the rate times the time. The principal is the amount of money that you're either investing or you're borrowing. The rate, well, it's your rate, it's your percent. Make sure that your rate is always, when we're calculating it, it should always be written as a decimal, and time should be always converted to years. So our principal is that $10,000 right over there. Our rate, 7.5%. In order to take a percent and convert that to a decimal, you want to move that decimal place 2 times to the left, making this 0.075. And it says 2 years and 3 months. So we need our entire time calculated in years. So we have 2 years plus 3 months. Well, 3 months out of a year. So 3 months out of a year is a fourth of a year. So we have 2 years plus a fourth of a year. So we really have 2.25 years that we're working with there. So our interest is equal to principal times the rate times the time. Multiply this all together, and that will give us the interest for this problem. Now I am going to be throwing this into a calculator here. So we do 10,000 times 0.075 times 2.25. It tells us that the interest for this after that 2 years and 3 months will be $1,687.50. So that answers the first question. How much interest will they receive? Well, this much here. How much money will be in their bank account at the end of that? So keep in mind that they started with $10,000. This is the interest that they've earned. So we're just going to take that. We're going to add in the initial $10,000 to it. So 10,000 plus this answer here for a grand total of $11,687.50. Our next type of example here is we're going to look about compound interest, and if it is being compounded annually, so just once a year. So if you notice here, principal is still P, R is still the interest rate, T is time in years here. So let's take a look at this first example here. Juanita deposits $8,000 into a bank account at the interest rate of 7.5%, compounded annually for 5 years. So the fact that they are telling you compounded annually is your big sign that you are using this formula right over here. So taking a look at this formula. So let's go ahead and throw into the formula here. This says A is equal to our principal, which for this problem is 8,000. Open our parentheses, 1 plus our rate. Our rate is 7.5, just like it was up here. So that is going to be 0.075 there for our interest rate. Raised to the tth power, and that says for 5 years here. So let's see, I am going to go ahead and throw this into the calculator. Let me put that to where there's not a lot of glare on that. So I'm going to calculate, let's see, I'm going to do the exponent portion first. We have 1 plus 0.075, close your parentheses, and raise that to the 5th power. And then I'm going to multiply that by that 8,000. So that is telling me that there is $11,485, and we're going to round that to 3 cents there. So that is how much money is in the account plus the interest at the end of the 4 years. So our second question says, how much interest does she actually receive? So in this instance, we're going to take this amount here, which is the total at the end, how much you initially put in, plus the interest that was earned. So if we want to know just the interest that was earned, take this dollar amount and subtract the $8,000 that she initially invested. That's going to leave us with our interest, which is $3,485.03. Now, in the world of investing, financial math, there's a lot of different interest problems, just really depending on the situation. So, our next one here is compound interest formula. So, this is where interest is going to be compounded multiple times throughout the year, right? So, we talked about simple interest, we talked about compound interest where it just happens annually. Now, we're going to be talking about what if it's compounded multiple times in the year. So the only new variable here is going to be the n. N is how many times it is compounded in a year. Otherwise, all the other components are staying the same. So let's go ahead and jump into this problem here. We're going to calculate it twice. The first time if it's compounded quarterly, second time if it's compounded daily. So this one reads that if we have $5,000 deposited into a bank account that pays 6.5% annual interest, find the future value after 1 year if the interest is compounded quarterly. That $5,000 is going to be our principal. 6.5% is then going to turn into 0.065 for our decimal there. Our time, it says 1 year, so our time is just going to simply be a 1. And if it's compounded quarterly, there are 4 quarters to $1. That means it is going to be compounded 4 times a year for our n. So let's plug into that formula. This is going to look like our principal, which is 5,000. Open your parentheses, 1 plus your rate, which is 0.065 over n, and we're compounding 4 times here. That's going to be raised to the n times tth power. So n is our 4, t is a 1, so that's really just to the 4th power there. Now, I like to simplify this just a little bit before throwing it all into the calculator here. So I like to simplify the inside of this a little bit first here. So I'm going to move that 5,000 over, and I'm going to clear up this inside here. And then after we take the 0.065 and divide it by 4, let's add that 1 to it. And for the inside of the parentheses, we're getting 1.01625. Don't round it quite yet. You don't want to round it to the very end. And this is all being raised to the 4th power. So if I take $5,000 here and I multiply that by the 1.01625, and I raise that to the 4th, it looks like it will be $5,333.01. Always make sure that you do round to the nearest cent there. All right, so that is how much is going to be in that account after that 1 year from initially putting in 5,000. So it's had an increase of $333.01 in a year, which is not that bad. Now, what's going to happen, or how much is it going to change if we compound this daily? Now, if we compound this daily, keep in mind that that n is the number of times interest is compounded each year. So we always assume a 365-day year for these situations here. So we don't necessarily take the leap years into consideration for just most general problems. So if it is being compounded daily, that is going to be 365 for our n. So we're still using the $5,000 as our principal. 1 plus, again, our rate is still going to be the same, the 0.065. That's now going to be over 365 raised to the, 365th power times 1. Doing some simplifying here. So let's see. I'm going to simplify the inside. We have 0.065, right? Our numerator here, divided by 365. And we're going to add the 1. So the inside of our parentheses is going to be 1.000178082 raised to the 365th power. So I'm going to go ahead and take that, raise it to 365, then multiply that times 5,000. So our end total here, $5,335.76 is what we get there. So really not too much of a difference between these two. For our next type of interest, we're going to talk about continuous compound interest here. So we see what that formula looks like right over here. So P is still our principal. E, again, as our designated variable, equals about 2.7, approximately like 2.72, but really 2.718, so on and so on. It is a repeating decimal just like pi. R is our rate. T, again, is our time in years. So going straight into this problem here, it looks like our principal is $9,000 times e to the r-teeth power. So if we take 6% as a decimal, that is 0.06 times our time, which is 8 years and 3 months. So again, that is 8 years plus 3 months. 3 months is 1/4 of a year. So that's 8 years plus that 1/4 of a year, making that 8.25 of a year. Let's go ahead and just throw this into the calculator here to see what we get. So we have E raised to, so let's do 0.06 times 8.25. And then if we multiply that times the principal, which is the 9,000, we are looking at here. This looks like it is $14,764.48. Our last couple of problems are going to deal with exponential growth and exponential decay here. So before I get into that, let's go ahead and read the problem and see what we're looking at. In the year 2000, the human population of the world was approximately 6 billion. Assume the annual rate of degrowth from 1990 onwards at 2.3%. Using the exponential growth model, estimate the population of the world in both 2030 and in 1990 here. So we want to use the exponential growth model here. So A of t, where t is the amount of time here, is going to equal to a sub 0. A sub 0 is the initial amount here. So what that means here is they're wanting us to find the population growth here. So a sub 0 is going to represent the initial population that we're talking about. And this problem starts off with saying that in the year 2000, the population was 6 billion. So think of the year 2000 as year 0. That is our starting point. And in that year, we had 6 billion people in the world. Okay, so time would be 0 for that situation. A sub 0 is our amount that we're talking about. So that's going to be a 6, just with the understanding that this is going to be in billions. Times e to the k-teeth power. Now, k is our rate, and it's giving us 2.3%, or as a decimal, that is 0.023. Times t, so times our year here. So that is actually going to differ here, because if we do notice, we were given two different problems. Find the population in 2030 and then in 1990. So this is our basic formula that we're going to be using here. The only differences here is we are going to calculate one for the population in 2030, and we're going to calculate one for the population in 2010. Now, if we're going to be calculating the population for 2030, again, think of the year 2000 as our 0 point, right? Our starting point here, our origin. From 2000 to 2030, that is a difference of 30 years, right? So it's really that difference of 30 years is our time. 30 years has passed between here and here. So time is going to be 30 for this one. So we're simply just going to plug that in for our t, and we're going to calculate that. So since we're going to be taking a look at the population in 2010, again, from 2000 to 2010, that is a difference of 10 years. So we're going to plug in we're going to plug in 10 for our time here. So 6e, we're using the same exact rate, but now times 10. So we're just going to throw this into the calculator here. So that's going to be e to the, we're going to multiply 0.023 times our 30 years, and then multiply that by the 6 billion. And when I throw that all into the calculator for this first one here, I am getting 11.9623 billion, right, for that population growth there. Now, if we do the same thing here, if we do the same thing here for 10, so let's see, that's 6 billion times e raised to the 0.023 times our 10. It looks like this is going to be 7.5516 billion people in that time. For our last example here, we are going to be looking at, let's see, you buy a fishing boat for $22,000. Your boat depreciates at the annual rate of 18% of its value. Find the depreciated value of your boat at the end of the 6 years there. So when we plug into this formula here, our a sub 0, again, that's always going to be your initial value, your original value. So in this instance, we're talking about how much does a boat depreciate. So its initial purchase amount was $22,000. All right, so that's going to be our a sub 0 times e to the negative k times t. It tells us that our k, 18%, or as a decimal, is going to be 1.8 times t. So the number of years, it wants to know how much it's going to depreciate after 6 years. So we can throw this straight into the calculator here. Times e raised to the negative 0.18 times that 6 years is going to give us $7,471.10. So that went down pretty drastically there.